So we can start now. Very good afternoon to the invited speaker, Dr. Ujjwal Dash, conveners, all the participants and organizing committee members. Now we'll start the second day of the two-day international webinar on development in technology, role of fiber optics and solar energy. Our invited speaker, Dr. Ujjwal Dash, has already joined 10 minutes before 4 p.m. Now I want to say a brief introduction of Dr. Dash. Dr. Dash is an associate scientist at Institute of Energy Conversion IEC at the University of Delaware, USA, with joint appointment as associate professor in the Department of Electrical and Computer Engineering and Material Science and Engineering. He received his PhD degree from India. He worked at the Indian Association for the Cultivation of Science, Jadavpur. He has achieved Best Presentation Award in National Solar Energy Convention, Young Scientist Award from the International Union of Crystallography, Young Researcher Award from the Japan Society of Applied Physics. He is the peer reviewer for grant funding of US Department of Energy and served in committees at UD and international organizations. At the University of Delaware, Dr. Dash and his group has first proposed and demonstrated a new solar photovoltaic cell architecture, namely IVC silicon heterojunction cell that is widely believed to be the ultimate high-efficiency silicon solar cell design. He has co-authored more than 95 peer-reviewed papers. He has also won US patent. He will deliver a lecture on role of solar energy in sustainable development. We know that solar energy is abundant and renewable energy source which is free. Solar cell convert solar energy to electricity. This is pollution free and causes no greenhouse gases after installation. Now our speaker will explain it thoroughly and he will highlight the importance of solar cell for sustainable development. Participants, you can write your question in the chat box just after completing his lecture, or you can directly ask the questions. Dr. Dash, please, you can start now.
Thank you, Dapati. Is it audible to
It's
audible for everyone? Okay. Thank you, Dapati, for your brief and kind introduction, and welcome to our today's talk on solar energy and sustainability. But before I get into that, let me handle a little technical issue here, and I'm trying to share my slides.
Yes.
Can you all see my slides? Okay, that's great. Again, thank you, Dahuti, for the introduction and welcome to the seminar. So before I begin talking about the topic, today's topic, which is role of solar energy in sustainable development, let me briefly introduce ourselves and where we are, who we are, and what we do. So we are, means the Institute of Energy Conversion at the University of Delaware is located in a small town called Newark, Delaware, which is shown in this bottom image at the right of the middle. We are approximately in between city of New York and city of Washington, D.C., which are both about 2 hours away from us. And as you know, the New York is the economic capital of the United States, and DC is the political capital of the United States. So we have a lot of influence both in terms of economics and politics. The Newark city, town of Newark is a small town. It's based on mainly university-based town, and at the heart of the town is the university campus, which is shown in the top picture here. And Institute of Energy Conversion, is located right at the edge of the right side of that image, with a square building, IEC. We are one of the oldest research institute dedicated for solar photovoltaic research and education. And the IEC was established in 1972. So we are celebrating our 50 years of research, innovation, education, and supply chain support for the US and international solar electric programs and the PV industry for over the last 50 years. We are basically a multidisciplinary team of scientists, engineers, postdoctoral fellows, graduate students, and undergraduate students from multiple disciplinary. That includes physics, chemistry, chemical engineering, material science, electrical engineering, and few other departments like environmental science and policy institute. So with that, let me start talking about today's topic, which is the role of solar energy in sustainable development. Now, there are seemingly two jargon words here. I'm not sure how many of you are familiar with these two words. One is sustainable development, another one is solar energy. So that's exactly what I'm going to talk about today. Uh, I'll start with what I mean by sustainability and how the solar energy can achieve the sustainability and what are the relationship between those two. So sustainability is philosophically, it defines that sustainable growth means you need to achieve societal development at the same time with an economic growth, but without affecting the environment. So the top left cartoon shows there are three things: the environment, society, and economics, and they all are interconnected. And right at the center of this, the intersection point is I define as a sustainability. So you want to achieve all three at the same time to get a sustainable development. Unfortunately, those three things are interrelated, interlinked. So if you change one of them, the other two will also change. So that's sort of shown in the right side image. So what I mean by that is if you start growing your economy, means you need better development and you need to have a lot higher or a lot more energy uh, to get that development. But the process and the process that we use to generate that energy, it affects environment. It also affects the human lives. So that's the equity and the society. So let me first talk about changing environment. Now, is it if we do development, human development or societal development, does it really change environment? So the graph here is showing a plot in the warming climate. The climate temperature is increasing over the past 200 years or so. So the graph is plotted from year 1850 until today. And we can define from 1850 to 1900 was the pre-industrial era. So where in that time, there was not much industry. And then from 1900 until today, we are continually developing our society with the help of industrialization. The figure here shows it has an important message. What is that our planet will warm gradually, but if we consider only the natural factors, it does not increase substantially, which is very flat, um, shown in this blue curve. However, we do see in reality a sharp increase in the average global temperature from 1900 and onwards. And this can be achieved or this can be simulated only if we consider human factors, means a human influence. So, what do we mean by the human influence in climate? Um, this cartoon, two cartoons here, shows a rough idea how we change the climate. So, as we industrialize our nation and the society, we need more and more energy and power. And currently, the way we generate and use the energy is using mostly by thermal energy, thermal power plant. And those thermal energy is basically a burning coal, means carbon. And while when you burn carbon, it will form CO2, carbon dioxide, and methane gas. Now, both are very good reflector of infrared light. And what happens during the daytime when the sun shines, it hits up the Earth's atmosphere and the Earth's crust, and some of the infrared light goes back to space, reflected back to space, but as we increase these pollutant gases like CO2 and methane, these reflects this heat back to the Earth's surface, and that's how it increases the temperature in the Earth's surface. Basically, those infrared lights, some of the infrared lights gets trapped into the Earth's surface and heats up the surface. So, what are the can we see that warmer climate and the result of it? So this, I am showing the two pictures here, two photographs. One was taken in 1918, it's early 1900s, near an Arctic, near North Pole in the Arctic Ocean, just north of Norway, in summertime. You can go to this place only in summertime because on other times the entire region becomes frozen and there's no way to get there. Uh, there is a group of scientists from Norway was able to travel to the same spot that you see in 1918 this year in the summer. And you can clearly see in 1918 there was a big iceberg that you can see and on mountain peaks on the distance. But this year, if you see that the iceberg is completely melted. It's a melted glacier, and you can clearly see the mountains. So definitely, the temperature has risen, and ice has melted, and this ice melt increases the sea level, and that in turn creates a warmer ocean and warmer weather. Well, the warmer climate, is it bad? So I'm showing a cartoon here. It's a conversation between two polar bears. It's good for the polar bears because the polar bear can now get their prey easily. One polar bear is saying that there you see, with the snow melting, he can't hide. He can't hide from us. Means the prey here can't hide from them. And you said global warming was a bad thing. Well, it's good. It may be good for the polar bear, but there are a whole bunch of things. Other things happen. First of all, it creates this warmer climate creates stronger hurricanes, more frequent flood, bigger wildfire, longer drought, hotter weather, stronger snowstorm, and all of these phenomena is very disruptive to human life and civilization. So here are some examples of the warmer climates and these natural disasters. As all of you know, recent flood in Pakistan. You may not know this year one of the biggest and the dangerous wildfire in U.S. in California. We are also showing a longest drought in U.S. in other parts of the region, U.S. region. Last year we have seen biggest snowstorm in Japan, and a couple of years ago we have also seen a mega hurricane Dorian, which was the biggest hurricane that we have ever noticed or encountered. So all of these phenomena we believe is related to the warmer climate. So I hope I was able to convince you now that the human caused pollution that creates warmer climate, and the warmer climate melts ice and sea level rise, which causes natural disaster. Now, if you continue this cycle forever, our Earth will be unlivable in less than 100 years. So, which is definitely not sustainable. And we need to act very aggressively now, and we must reduce this carbon pollution. Well, the big question now, how to do that? Remember, I showed you the human influence in climate. We want industrialization, we want development, we want economic growth, but we don't want to release CO2 and methane gas into our atmosphere. So we need to focus on the middle part, which is the energy and power, and how we generate them and how we use them. So what are the options? First of all, let's go back and look at how much CO2 emission we are making by energy sector, different energy sector. So this graph is showing different energy sector means electricity generation and how much CO2 it emits per year. Um, Also shows the transportation, industrialization, buildings, and agriculture. One thing you notice that the electricity generation was the highest carbon emitter by far until around 2005, 2010, but it has slowed down and it gradually started to decrease. So we are doing good for electricity generation to curb carbon pollution. But as you notice here, we haven't thought too much about the other form of uh, energy sector, which is transport, industry, building, and agriculture. So what are our options? First of all, if we look at the energy sources available to Earth, as I said before, that most of the time we generate our electricity from coal. And here I have shown the reserve or the sources amount of the source that's available to us. For coal, it's pretty big, so we should be able to last for a long period of time. And by the way, the current world energy consumption per year is about 16 terawatt. By 2050, it's supposed to go up to about 30 terawatt. Now, coal has a reserve for 900 terawatt of power. So, coal is definitely enough to sustain for another century or so. Uh, but coal is the worst carbon polluter, as we know it now. And to changing from coal to gas, which is also another carbon-based fuel, it does change the carbon emission a little bit. But more cleaner option is either nuclear and the solar and wind. The nuclear does not create any greenhouse gases, but it has other disadvantages. Like it still has a finite source available to us. But if you look at the solar, we have about 23,000 terawatt per year available, and it is sustainable. So solar by far the most abundant, and we can meet the global energy demand if we can capture only 0.1% of the incident solar energy. Or in other words, we can say if we can capture 1.5 hours of solar, that can give us energy equivalent to 1 year of global energy use. So that's a huge potential for energy source. And as you know, solar is essentially sustainable, means as long as the sun shines, we will be here. But when the sun dies, everything will fall apart anyway. Well, so I say that it's good that we have raining solar energy, but it's very bad that we don't use it. So this is where I want to focus on. How do we capture the solar energy? There are fundamentally two technologies that we have come up with. One is called solar thermal technology. Another one is solar photovoltaic technology. In solar thermal technology, when the sun shines, the sunlight gets reflected by mirror to a tube that has a fluid that absorbs heat. So that sunlight hits the fluid, and that heated fluid converts water to steam. So we need a heat exchanger in another step, where we flow water close to that heated fluid, and that steam generates electricity through turbine. So it has multiple steps, but it's a simple technology. On the other hand, the solar photovoltaic technology basically sun shines on a piece of semiconducting diode, and it creates electrons. Um, so electrons flow is the current and electricity. So it's a direct conversion of sunlight to electricity. So now for rest of my talk, I'll be mainly talking about the solar photovoltaic technology, not too much on solar thermal. Okay, so now if we go back and look at the solar PV journey, from 1972 when IEC was established until for next 2 decades until 1992 when I started my research career. In 1972, most of the energy was converted using a thermal power plant, which is shown in this picture. And you can see the smoke. Those are the CO2 and methane particle coming into the atmosphere. And then if we fast forward to 1992, by the time I joined as a research fellow in Jadavpur, there are already some solar product, and there are two types. One, the bottom one is showing an isolated remote niche application of solar panel, where you can see if there is a remote place where you don't have any electricity grid line available, you can power those homes using these small solar panels. This is mostly attractive for the developing world at that time, but in the developed countries, they already started building this big solar plant and started using it as a grid connected electricity source. So now if we fast forward to the 21st century, we see a little bit of challenge. The figure shows here the carbon emission from 1992 until about 2018. In the middle, you see the two region where the developed countries, they are able to maintain the same level of CO2 emission or maybe have reduced a little bit over the last 30 years. But there are some developing nation means they are developing and they are increasing their industrialization. And as a result, they started to produce more CO2 emission. And what we see overall, it started to increase the CO2 emissions. So we can clearly see that currently we don't have a sufficient clean energy production to reduce or to curb the CO2 emission. So that's where we need to focus on, and it's a climate urgency at this point. Um, so before I, well, so what can we do to curb this pollution and to help the planet sustainable? Um, First of all, there are few aggressive actions needed. Now the question is where to focus. So in this pie chart where I'm plotting as a global CO2 emission by energy sector currently, and as you can see, the electricity and heat generation and distribution is the most contributor, which is about 25%, followed by agriculture sector, and then industry and transport. Now, to reduce or to affect all of these influences, we definitely need policy changes and the economic considerations. So policy and economics plays an important part uh, to make this sustainable. So now I'll go little in next few slides. I'll go a little bit about science, that what we do every day, but not too much into details. So first, I want to describe a little bit how can we generate electricity from solar. So if we need to understand that, we need to look at the inside of a solar cell or solar panel. What happens inside there? The solar cell is basically a PN junction diode, as is shown in this cartoon here, um, which is photoactive. So what it means that this diode, many of you may know may have studied in the electronic class about the diode, PN junction diode. But this diode is photoactive, means when you illuminate, it creates more electrons. Um, Briefly, I explained a band diagram here. I'm not sure whether everyone understands the band diagram. So this is a PN junction diode. And when you bring a N-type semiconductor in close contact with P-type semiconductor, it forms an electric field and bends the band. So the electron can go only downwards. So once you create an electron, these electrons will separate out from where it's created and flow in other direction. And that flow of electron forms a current because as you know, you may have studied that dq dt is the current. So to describe a solar cell, a simple equation is this one, which is the current is equals to the light generated current minus there are some loss in current due to that transport. And that is an important contributor to think about how do we generate or how do we design our solar cell to work more effectively. The bottom shows a standard IV curve under illumination, and you can see the if you the product of current and voltage is the power, and the power is plotted in a blue curve here. And you can see at certain voltage you can get a maximum power output. So that's where you want to operate your solar cell. So now let's look at a little bit more science of a solar cell. As I said, the main driving equation for solar cell is as it's shown here. You want to maximize this light generated current. So you have to minimize this term, the I0 term. I0 is one of the key parameters in solar cell. And it's a measure of recombination loss in solar cells. That's a loss mechanism, and you want to minimize or reduce and ideally make it zero. So all solar technology tries to reduce this value of I0 to increase power. So that's why there is a significant technology development needed to achieve this. So what we do here at IEC, we look at a few different technologies. Two is two more or two best commercial solar technologies, silicon and cadmium telluride, best material. Now, these two technology contributes about 97% of solar energy produced today. So improving the performance of these two technology have a big impact. How do we generate and how much energy we can generate? So in both cases, we focus mainly, as you know, that as I mentioned earlier, that we mainly focus on to minimize that I0 term or the recombination loss term, or in other words, to reduce the defects. So in silicon, we use several different concepts to develop this. On cadmium telluride, we also use some like doping and other things and the defect passivation to improve the performance. I'm not going into details about this. The other technology, recently in the last 10 years or so, there is a very important material came up, which is called perovskite. It's an emerging technology. And the advantage of this material is it's inherently low I0. But it does have other challenges. First of all, you need to develop, it's an emerging technology, and you need to develop these or grow these films as fast as you can, as big as you can. And that's where there is a lot of challenges, processing challenges that we are addressing. And it also has significant stability issue, means it degrades very rapidly in humidity. But since the solar cell has to operate outdoor, it will have a significant issue for temperature and humidity. Anyways, but these are the solvable problem. That's why the scientists are working on it to implement, to bring up this technology. And finally, I believe this should be this probably the ultimate technology that's going to, you might be able to see it in next 10, 15 years, which is called a tandem solar technology. Just basically is merging those that emerging perovskite technology um, with another cell with a current silicon or cathode technologies to improve the performance. But anyway, I'm not going into details of this performance. There is another thing to consider is the solar economics. So in this plot, on the left plot, I'm showing a solar module price over the last 10 years. And you can see this blue line here, it drops by about an order of magnitude over the last decade. So there is a precipitous drop in solar module price. It's a low cost energy, and it's considered as a low cost energy solution in many places globally. But it depends on the price of the coal energy. So in the right plot, I'm showing the installation of the PV installation over the last 10 years or so, and you can see an exponential drop in cost as we increase the PV installation. So this low cost is primarily due to two things. One is the exponential growth of solar installation, which is still continuing, and the technology development. But this economics brings up another challenging concept that any new technology that's are developing in research and development at this stage, to enter the PV market, it needs to meet this low cost energy structure, which is a very challenging task for a new technology because we already have over 1 terawatt of solar installation globally, and no one is going to replace those solar panels in next few months or so, because this solar once you install a solar panel, it mean to last for at least 25 to 30 years. So any new technology that is being developed in the lab today might see the market after, let's say, after 20-25 years as a replacement of this old technology. Okay, so now I'll go a little bit more about the energy distribution. So we generate a lot of electricity, but solar electricity is a DC. How do you connect to the AC grid lines? So if you go from the left part of a solar electricity generator to the right part of the local grid supply, there are a lot of electronics that you need to integrate in between. And IEC is also actively working on all of these components. So there are a lot of research needed to figure out how to effectively connect a solar into a PV grid lines. The another topic I'd like to touch upon is the agriculture. Um, in many places internationally, it has been seen, it has been observed, or the politics have been enforced that agriculture and technology can't go hand in hand. So they are like opposite. Solar actually provides you that opportunity to have both agriculture and electricity or the energy generation at the same location. And here are a few concepts which is called is agrivoltaics. It's a whole new topic currently, and it provides a controllable shade and full sun as needed seasonally. It helps keep farming profitable because it can optimize the growth of the farming and the crops. And it also, as I said, it's a dual use purpose, so it avoids the land use conflicts by many uh, political development. The other big energy sector that needs to be decarbonized is the transportation. Well, if you think about it, this low duty vehicle, it's very easy to be decarbonized. So you can just use the electric cars, and a lot of things are happening in India too, um, using electric vehicles. So you can directly charge a DC solar energy into a DC battery of your vehicle. But to totally decarbonize the transport sector, we need a lot more than that. Drawing from NREL, that's the National Renewable Energy Laboratory in the US, has made this cartoon. So you can have a renewable electron here which can directly charge your low duty vehicles, but it's probably not going to sufficient to charge a rail or a high heavy duty vehicle or a ship or an aviation or an airplane. So to do that, you need to go to an intermediate energy system, which basically generate, let's say, hydrogen or liquid fuels using these renewable electrons. So all of these research are needed, and there is very few application at this point or in the market, but it's still on a research and development stage. Okay, so now I'll, I'm coming to the almost to the end of my talk. So let me briefly describe what we exactly do at University of Delaware and at IEC. So we have a significant effort for sustainable energy education, where we have different departments teaching about the PV, wind energy, batteries, electronic vehicle, EV, charger, and the economics and the policy. And our goal is to connect all of these to a clean, sustainable grid. And what we hope is when a student graduates, he'll go into various places and save the world. So that was my talk. And I'll be happy to take any questions if you have one.
Thank you, Dr. Dash, for your innovative, informative, and encouraging session. We are enriched after your excellent lecture. Now the session is open for discussion. You can ask if you have any questions. You can write in the chat box or you can directly ask him. If you have any questions, I want to know a little bit about perovskite solar cell.
Yeah,
Because
sure.
it was not in my part during research.
Yeah. So what is the question actually?
What is basically perovskite?
Oh, okay. The perovskite is it's basically right now perovskite is a crystal structure named after a scientist called perovskite. Um, he was a Russian scientist. It was discovered in, I believe, in early 1900s. So it's basically a structure called calcium titanate that you can get in a lot of mines. Uh, but calcium titanate is actually an insulator. It's a high band gap. So in last 10 years or so, people started thinking about that structure, crystal structure, and they replace few of those components and make a hybrid inorganic organic structure. Basically, it's a lead iodide is a primary or inorganic structure, and then they mix like methyl ammonium and lots of organic molecules into it. And of course, this was discovered by some chemists because uh, they can introduce many different molecules and other things into the crystal structure. So it's basically the structure is methyl ammonium lead iodide. The perovskite name is the structure, crystal structure. It's not really a material. It can have perovskite structure on multiple different materials, but it turns out that methyl ammonium lead iodide has the correct band gap so that it can absorb solar energy. Um, the band gap is about 1.6 eV or so. So basically, it started. Best, I consider it is an ideal match between a chemist and a physicist, because the structure was discovered by chemists, and when they joined by a lot of physicists, they are able to make efficient solar cells because Physicists knew how to extract those electrons and holes, but the chemists knew how to introduce more organic molecules. So it's a very complicated structure, but it has a flexible structure. So you can control the defect levels, band gap, and lot of these properties. That's why it's very attractive. And it has been demonstrated solar efficiency as close as silicon solar cell.
It can match with silicon, and we can
Yeah,
go for the heterojunction solar cell.
yeah. The band gap, as I said, the band gap is tunable depending on what organic molecules you are putting into it. So the band gap can be varied from 1 eV to anywhere up to 3 eV. So when you put into a silicon cell, you can choose your appropriate band gap.
Okay. As this lecture is on solar cell, so I want to ask, what is the disadvantage of hydrogen fuel cell
Uh,
compared to the silicon solar cell, compared to solar cell?
well, fuel cell is not it's a storage system. So basically, uh, it generates fuel, but that fuel has been a little bit stagnant, means there is no new discovery, and its efficiency is still pretty low. But the fuel cell can be used. It's not uh, contradictory to solar cell, but it can be complementary to solar cell. You can use fuel cell to store a solar energy or solar electricity.
Okay. To store the solar electricity. Okay.
Yeah, like well, solar has a one big problem, right? It shines only during day, not in the night. But we use energy, a lot of energy at night. So the solar energy has to be stored somehow, somewhere. So options are there's the batteries that we use, or maybe a fuel cell.
Okay. Nowadays, whatever photovoltaic energy we are generating, we can transmit it to the CAC or anywhere through the grid. It is already done. So we are looking for more
It's
details.
yeah, it's not really done. The grid integration is a big challenge at this point. It's done. If you remember, the solar electricity is probably about 2 to 3% of the global energy supply. The question is, how can we get to 50% or 100%? And the solar electricity has a big problem with the intermittency, means the sun is not at the same intensity always, and that provides a lot of problem to the grid operators. So the grid can tolerate up to a certain percentage of these uh, intermittent electricity, but not 50. Grid is not designed for even 10% or 20% of solar electricity.
Okay, that's why you are not getting any problem. We can easily transmit it to the electricity board.
Yeah,
Okay,
because
there is.
because China is only less than 1% probably.
1%. Okay, thank you very much. I think Abro Giri has some questions. Abro, you can ask now.
Thank
You have
you, Dr. Das, and it is very informative talk. But I want to know what will be the uh, future cost or the maintenance cost of uh, the device developed to store or to transmit the energy from the harvested area to the tower or AC tower. So,
Mhm.
what will be the maintenance cost per year or etc.?
That's a very good question. So now, as I shown you, let me see if I can share the screen again. Okay, can you see my screen?
Yes.
Okay. So your question is, so we go from here to the local grid, and what would be the maintenance cost for the entire system? Is that right?
Yes.
Okay. So as I mentioned, there are a lot of different electronic components. The maintenance cost for solar is almost nothing. You may need to occasionally clean the surface, basically blowing or washing with water. Uh, the advantage of solar panel is that it has no external moving parts. The only moving part is the electron, which is inside the semiconductor. It does not degrade or decay anything, unlike all other forms of energy, like wind, thermal, nuclear. They need to have turbines and rotating things. So it does not have any too much a maintenance cost for the solar panel itself. But there will be maintenance cost for other things. For example, if you use a battery to store the energy, the battery technology is not matured enough, so you need to replace the battery every 10 years. And of course, there are a lot of electronics, the inverters, and for example, if you use a EV charger, most of them last for 10 years. So in terms of maintenance cost, I would assume it's mostly because of these uh, intermediate accessories that you need to put in. If you can connect PV with just an inverter to a local grid, that's how US is doing for almost all rooftop solar. It has only three things: a PV panel and a solar inverter, and that connects to the local grid. So the only maintenance cost is the inverter, and inverter technology is improving very rapidly. I'm not sure how long the new inverter lasts, but old technology, like 20 years old inverter technology, used to last for 10 to 15 years. So you have to replace that. What that means is you have to replace that inverter every 10 to 15 years. Does that
Okay.
answer your question?
Is there any more questions? Please ask all the participants. Okay, if there is no more questions, so thank you, Dr. Das, once again. So you have explained very nicely that use of solar energy is the best solution to reduce the global warming and climate change. And thank you very much for your presentation.
Thank you, and have a good night.
Thank you. So
Thank you.
all the participants, before you you can the feedback form is already given in the chat box. You can just fill up and submit it.
Prabhuti, Joyita will give vote of thanks.
Oh, okay, sorry. Now Dr. Joyita Chatterjee will give the vote of thanks. Dr. Joyita Chatterjee, please. Oh, this is my mistake. Joyita, please.
Thank you, Tapotidi. A very good afternoon to our eminent speaker, Dr. Ujjwal Kumar Das, and my colleagues and dear participants. I know I stand between you and the end of this seminar. So before I let you go, I would like to thank all of you for your contributions. First of all, our principal ma'am, Dr. Urmila Ukil, for her guidance and support. Next, our IQAC coordinator, Dr. Sudeshna Chatterjee, she always encourages and motivates us to arrange this type of seminars, which will be beneficial for the students. So I thank them on behalf of the Department of Physics. My special thanks to the eminent speaker, Dr. Joy Shankar Roy from Laval University, Canada, and Dr. Ujjwal Kumar Das, University of Delaware, USA. Both of them have provided us their valuable time and from their busy schedule, So I really thank them, and please accept our gratitude for your presence. And you, both of you, have explained these modern topics, most emerging technologies in modern times, that is fiber optics and solar energy. So both of you explained it in a very lucid way for the students. So I really thank both of you. Now, I would like to thank our convener, head of the Department of Physics, Dr. Enakshi Guru, and on behalf of Department of Physics, Dr. Obhrogiri and Dr. Tapoti Jana. Both of them have already, without them, it was very difficult to organize this seminar, especially Dr. Obhrogiri. I would like to thank you for your support and generous contribution, without which it would be difficult to organize this seminar. I would like to thank all the organizing members of this seminar, and especially I would like to thank the participants who followed the webinar enthusiastically for the 2 days. So thank you very much. I hope you have enjoyed the seminar. Thank you.
Okay, thank you.
Thank you.
Jalda, one more time.
Yeah,
Okay, thank you.
Participants, please fill up the feedback form and then you leave.
Otherwise, you won't get the certificate.
All of you, please fill up the feedback form so that we can give the certificate for this.